Welcome to the new era of video creation with Bias 8. Today, we will discuss the bias-variance trade-off. Question: explain the concept of bias-variance trade-off and how would you handle it during model training? The bias-variance trade-off is a fundamental concept in machine learning that deals with the relationship between model complexity and the performance on both training and testing datasets. Bias refers to errors that occur due to simplifying assumptions made by the model. For example, a linear regression model may oversimplify a relationship, leading to a high bias. Variance reflects how much the model's predictions fluctuate with different subsets of data. Models with high variance may overfit the training data, resulting in poor generalization to new, unseen data. The trade-off occurs because reducing bias typically leads to an increase in variance, and reducing variance may increase bias. Our goal is to find the optimal balance between the two, which minimizes the total error. This balance helps to build robust models that generalize well to unseen data. When discussing the bias-variance trade-off, it's important to distinguish between models with high bias and those with high variance. High bias models typically underfit the data. They are overly simplistic and fail to capture the underlying patterns of the data, resulting in poor performance on both training and test sets. Examples include linear models with too few features. High variance models, on the other hand, are complex and capture too much of the noise in the training data, leading to overfitting. They perform well on training data but poorly on test data because they fail to generalize. Examples of this are deep decision trees or high-degree polynomial models. To diagnose overfitting or underfitting, observe the training and test performance. Overfitting shows a large gap between high training accuracy and low test accuracy, while underfitting will result in both high training and test error, indicating the model cannot learn from the data. Graphically, the bias-variance trade-off is often represented as two curves. Bias decreases as model complexity increases because more complex models can capture more patterns from the data. Variance increases with complexity as the model starts to fit the noise in the data, leading to overfitting. The total error is the sum of three components: bias, errors introduced by overly simplistic models; variance, errors due to model sensitivity to the training data; irreducible error, this is the noise in the data that cannot be avoided or explained by the model. The optimal model lies at the point where the bias and variance curves meet, minimizing the total error. To reduce bias and mitigate underfitting, the model needs to be able to capture more complexity in the data. Here are a few approaches. Increase model complexity. If the model is too simple, e.g., linear regression, we can opt for more complex algorithms such as decision trees, random forests, or neural networks. These models can learn non-linear relationships and are more flexible. Add more features. By incorporating additional relevant features, e.g., through feature engineering, the model gains access to more information, which can improve its ability to learn from the data. Use non-linear models. If the data is non-linear, using a linear model will introduce significant bias. Using non-linear models such as kernel SVM or neural networks can reduce bias by better capturing the inherent complexity in the data. Adjust hyperparameters. For example, in decision trees, parameters like max depth or min sample split can be tuned to allow the model to better capture the data's complexity. To reduce variance and prevent overfitting, we focus on methods that simplify the model's decision boundaries, making it less sensitive to small fluctuations in the training data. Here are the common techniques. Cross-validation. By splitting the data into different training and validation sets, cross-validation helps detect overfitting and ensures the model performs well on unseen data. Pruning. In models like decision trees, pruning refers to the process of cutting down branches that have little predictive value. This helps in reducing complexity, which lowers variance. Regularization. Applying L1, lasso, or L2, ridge. Regularization penalizes large weights in models like linear regression, encouraging simpler models that are less likely to overfit. Ensemble methods. Techniques like random forests, XGBoost, or AdaBoost combine multiple weak models to create a more robust model, reducing variance and improving performance on unseen data. Hyperparameter tuning is an essential step in managing the bias-variance trade-off, as it directly influences the model's complexity and learning ability. There are several techniques to optimize hyperparameters. Grid search exhaustively tests all possible combinations of hyperparameters, e.g., learning rate, depth of decision trees, to find the best model configuration. While thorough, this can be computationally expensive. Random search randomly samples from the hyperparameter space and can be more efficient than grid search when the number of parameters is large. Bayesian optimization uses probabilistic models to guide the search for hyperparameters, intelligently choosing which configurations to explore next based on past results. It is more efficient than grid and random search. Early stopping is a technique used during training, especially in deep learning, where we stop training when the model's performance on a validation set starts to degrade, preventing overfitting. In practice, handling the bias-variance trade-off is an iterative and dynamic process. Here's how we approach it. Understand the data. Analyze the nature of the data before deciding on a modeling approach. For instance, if the data has lots of noise, a more complex model might overfit. Model selection. A linear model may be suitable for simpler problems, low variance, high bias, while tree-based models, like random forests, can handle more complex data, low bias, high variance. Iterative refinement. Model building is an ongoing process. We often need to retune parameters, adjust features, and iteratively refine the model based on error analysis and performance. Monitor overfitting. Use tools like learning curves to visualize training and validation error over time and detect overfitting early in the process. In summary, the bias-variance trade-off is at the heart of model selection and training. The key points to remember are: bias and variance represent opposing forces in model building. While we want a model that captures the complexity of the data, low bias, we also want it to generalize well to new data, low variance. High bias occurs in underfitting models that fail to learn the data's underlying patterns, while high variance occurs in overfitting models that are too complex and fit noise. A good model strikes a balance between bias and variance, effectively learning from the data while generalizing well to unseen examples. By using strategies like regularization, cross-validation, and hyperparameter tuning, we can handle the bias-variance trade-off and build models that perform well in real-world scenarios.